Hello guys, hope you all are doing well. So in the continuation of the previous GATE series, we were solving the question of 1990. So today we have a new question, and so today we have a question of heat transfer, which GATE had asked in 1990. So I'll write here 1990 GATE heat heat transfer question 14 part first. Okay. So without wasting time, we will go into the question. What question is saying? It will be visible to your screen. In a 1-1 shell and tube heat exchanger, steam is condensing on the shell side at Ts degree Celsius and the cold fluid is being heated on tube side from T1 degree Celsius to T2 degree Celsius. So we know that if steam is used as a heating medium, then the profile is like that. This will be the profile of steam Ts. Okay, and the cold fluid will get heated up. So initially the temperature was T1 degree Celsius. It is right now T2 degree Celsius. Okay, length of heat exchanger. This is the temperature T. Sorry. Here we have T. Okay, so this is the temperature profile when uh, the steam is heating medium. Now the question is saying the following equation relate T2 to the other variables. So we have an equation in the question ln Ts minus T1 upon Ts minus T2 is equal to UA MCP. U is the overall heat transfer coefficient, A is the heat transfer area, M dot is the mass flow rate, and Cp is the heat capacity. The tube side coefficient is controlling. This is very important information. Tube side coefficient is controlling. Just take care of the spellings. Okay. And the tube side fluid is in turbulent flow. Another important equation. Another important thing, information. Tube side flow is turbulent. Okay. If Ts is 130 degrees Celsius, T1 is 30 degrees Celsius, T2 is 80 degrees Celsius. And if mass flow rate of cold fluid is doubled while keeping all the other conditions same, find the new value of T2 at steady state. Okay, so we have given the value of Ts is equal to 130 degrees Celsius. Then we have T1 30 degrees Celsius. Then we have T2 that is 80 degrees Celsius. And it is saying in the question if mass flow rate at the second condition is twice the mass flow rate which is used in the first condition, then the value of T2. Okay, so very first thing, it is saying that tube side coefficient is controlling. That means we know that the overall heat transfer coefficient 1 by U is equal to 1 upon heat transfer coefficient of cell side plus 1 upon heat transfer coefficient of tube side, HT. Neglecting the here, neglecting the resistance of tube wall. ट्यूब वॉल का रेजिस्टेंस हम लोग यहाँ नेग्लेक्ट कर रहे हैं. ट्यूब वॉल जो कि क्या होता है L upon Ka. Okay, so because it is not given in the question, so we are neglecting it. Okay, otherwise there is a big formula for 1 by u. I will write here just for your information. 1 by u is equal to that is 1 upon h into r plus hf h hot into r I plus L upon Ka plus 1 upon h cold into r naught, kind of this formula we have. For heat transfer you can refer for heat transfer you can refer R.K. Rajput for numericals, okay, and J.P. Hallman for theory. J.P. Hallman is very good book, and for numericals R.K. Rajput is very best. A large variety of numericals are there. You need not to go anywhere for the numericals. Okay, so refer these two books. So coming back to the question. So it is saying that tube side coefficient is controlling. That means HS is very high and 1 upon HS will be 0. So tube side, where is the arrow? So since tube side coefficient is controlling, that means HS is very high, so 1 upon HS will be 0. So U is equal to HT. If it is written in the question that shell side coefficient is controlling, that means HT is very high and this is 0. 1 upon HT is 0. So now second information, tube side flow is turbulent. So for turbulent flow in tube, we have what we have? Dittus-Boelter equation. Dittus-Boelter equation. Just check cross check the spelling. So Dittus-Boelter equations is Nusselt number is equal to 0.023, Reynolds number 0.8, Prandtl number 0.4. Prandtl number is what? Reynolds number we all know. Prandtl number, remember from word P mot. P mot. That means Prandtl number equal to mo matlab momentum. Momentum matlab fluid mechanics, that is kinematic viscosity, and T matlab thermal, that is alpha. P mot and samoma, you can remember this as samosa. So Schmidt number is equal to SC, mo that is momentum, ma that is mass, DAB. Okay, and third one is ultima matlab Lewis number is equal to thermal diffusivity, that is alpha upon mass, DAB. Okay, so you can remember like this. So coming back to the question. So Nusselt number is equal to, what is Nusselt number? HD by K is equal to 0.023. Reynolds number is rho Vd upon mu 0.8 and Prandtl data remote. Okay, so I will write it like this because it will automatically cancel out. Because both the things are constant. Prandtl number will remain constant. Okay, now h dy k is equal to 0.023. Reynolds number is rho Vd upon mu 0.8. Prandtl 0.3. Sorry, for heating PR to the power 0.4, for cooling PR to the power 0.3. Okay, but generally we use 0.3. Okay, so 0.3. Okay, so 0.4. So now just rearrange this. That's all. 0.023. We know that velocity is what? In a tube or in a pipe, Q is equal to area into velocity. Q is equal to area is pi d square by 4 into velocity. 4q upon pi d square is equal to velocity. Put this value of velocity here. So rho d by mu into 4q upon pi q pi d square to power 0.8 Prandtl 0.4. Okay, now if I multiply density and Q, density is kg per meter cube into Q is volumetric flow rate meter cube per second, that will give kg per second, that is mass flow rate. Okay, now just replace it. H dy k is equal to 0.023. Okay, I will write this density and this Q. If I multiply, I will write 4m into d. I will cut this d from this d, so it will upon 4m pi d mu 0.8 Prandtl 0.4. Right, now h d by k is equal to 0.023 Prandtl 0.4. 4 upon pi d mu 0.8. I just take it out. I just take mass flow rate out. Okay, now h is equal to k by d 0.023 Prandtl 0.4 4 pi d mu 0.8 m 0.8. Okay. So k is constant, d is constant, pipe diameter, that this d and this d both are same. Okay, this d and this d both are same, pipe diameter. Okay, d is same, Prandtl number will remain same. Okay, pi is constant, d is same, mu is same. So I can write this whole term as big constant into mass flow rate 0.8. Okay, second equation. So this is okay. Now in the previous slide we have seen that U is equal to HT. Okay, So I can replace this u from ht in equation 1. Okay, I'll do that. So ln ts minus t1 upon ts minus t2 is equal to, I will replace u with ht. So ht and ht is same, area upon mcp. Okay, now I can replace this ht with this value k 0.8 area upon mcp. Just little calculation. Ka, here is power 1, here is 0.8, so it will go down as 0.2 cp. So our final expression is ln t2 minus t1 t sorry this ts minus t1 ts minus t2 is equal to constant a mass flow rate power 0.2 into cp. Okay, now this is first condition at original condition. Now the mass flow rate in the question, it is saying we are just doubling it. Okay, we are doubling the mass flow rate. So this is the condition. We are doubling the mass flow rate. Now we have the value of ln ts is 130 minus 30 upon ts is 130 and t2 was I think 80, yeah, is equal to ka. If this is first, then I will write as m1 0.2 cp is equal to ln 130 minus 30 100 and 130 minus 80 130 minus 30 50 50, that is ln2. So finally we have ln2 equal to ka upon m1.2 cp. We got this value. Okay, now at condition 2 to m2 is equal to twice of m1, first condition. Only mass flow rate is changing, everything else is same. So we have to find at this condition T2, new T2 at steady state. So ln 130 minus 30, everything is same, but we have to find T2 here into Ka upon m2 0.2 Cp is equal to Ka, m2 is twice of m1, 0.2 Cp is equal to, I can write like this, Ka twice 2 into 0.2 की power 0.2 m1 की power 0.2 into Cp. I have this value, right? Where? This, right? I have the same value. So just replace it. That's all. So ln2 divided by 2 to the power 0.2, 2 to the power 0.2. Okay. So we have ln 130 minus 30 130 minus T2 is equal to ln 2 divided by 2.2. Now calculate it. I can write like this: 130 minus 30 upon 130 minus T2 is equal to e to the power ln 2 divided by 2.2. This value, this whole value will come as 1.83. 1.83. Okay. So 130 minus 30, that is 100, divided by 1.83 is equal to 130 minus T2. So it will equal to T2 will come around 75.4 degrees Celsius. So this is our final answer. This same question with the different values GATE asked in 2016. That was my first attempt in GATE 2016. Okay, so previous year are very important, very important. They somehow just change the value and the question and the concept remains the same. Okay, so thank you guys. Hope you understood the question, and if you have any doubt or anything, just comment it below. I'll try to reply as soon as possible. Okay, thank you guys. Bye.